Hi everyone. I wanted to make this video because I talked to a number of you who felt that the 11.7 homework in particular was really challenging, especially the latter part of it. So like starting with problems 37 and on. And so I just wanted to make a video. The the solution guide has been available on Canvas for a while now. But I wanted to walk everybody through the explanations for these problems so that hopefully that kind of helps some of these questions to gel, since we will be using especially the chain rule in chapter 12 quite a bit. And so I want to make sure that that concept sticks with everybody and that we understand why we're doing it so that um, when it comes up again in chapter 12, it makes a lot more sense, hopefully. So here is what we're going to do. We're going to go ahead and start walking through these first few anyway, even though people mostly had questions about 37 and on, but we'll just start with the first couple. So looking at number one, when we're doing problems like this, we're given two functions, f of x and g of x, and we're supposed to find f of g of 5. So basically the way that these compositions of functions work, which is what these are called, this function that's on the outside is what we do last. The function that is on the inside, that's what we do first. So we need to find the value of g of 5. So when I go to the g function over here and I put 5 into it, what do I get out? And I can see what I've done here is here's my g of 5, right? So I'm taking that value of 5 and I'm putting it in for x in the function that is labeled g. So that would give me 4 times 5 minus 1, that's 19. And then once I get that value of 19, g of 5, that is right inside of the f function now, we actually know what that is now. It's 19. So really what I'm being asked to do in this problem is find f of 19. And so that's the very next thing that we do. We take the 19 and we plug it in for x in both of the instances of the variable x in the f function. So we have 2 times 19 quantity squared plus 3 times 19 equals 779 when we evaluate that. So that's how that first one goes. Problem number 3 is basically the same thing, and we're even still using the same functions. Only this time, when we're doing it, it is the f function that is on the inside, and then the g function that is on the outside. Okay, so I am going to go to that f function since we're starting at the inside, and I say, okay, I want f of 5. That means I'm going to grab the number 5. I'm going to plug it in everywhere I see an x in the f of x function. So I would have 2 times 5 quantity squared plus 3 times 5. And when I simplify that, I get a value of 65. And then that 65 is what we're going to replace the f of 5 with. So that means what we really want to find is we want to go to the g function and we want to put in the value of 65 where we see the x. So g of 65 would be equal to 4 times 65, because we're replacing the x with 65, minus 1. And that's where the 259 is coming from. Okay, so that's those two. Number 7 is very similar, with the exception of the fact that instead of being given a specific number to replace x with, we're leaving the x in there as just a generic variable placeholder. So let's see. I'm gonna get some more colors here. So our f of x function is 3x squared minus 8x plus 1, and our g of x function is x minus 4. Okay, so the very first thing we're supposed to find is f of g of x. So that means rather than replacing the x in the function f with just a particular number, we are going to replace every instance of the variable in the f function with the entire g function. And so, like when we're thinking about the f function, what does it say? Well, it says we take 3 times x squared minus 8 times x plus 1. Except each of those x's needs to be replaced with the g function, which in this case is x minus 4. So before simplifying, that means we would have 3 times the quantity x minus 4 squared minus 8 times the quantity x minus 4 plus 1. And then everything else we do from that point on is just simplifying. It's trying to make things look nice. So we're distributing to get rid of parentheses. We're combining like terms. That is what all of these next steps in the solution guide, that's what they're showing, is just the simplification part. But the actual composition of functions where we plug one function into another one, that happens at that very first step. The second part of number 7, we're finding g of f of x, which is the same thing, just in the opposite order. So we're actually going to start by taking the f of x function and putting it in for each x in the g of x function. So g of x said x minus 4, right? But we're going to replace the x with the f of x function, 3x squared minus 8x plus 1. Sorry. And so when we do that, what we can see here, so we have 3x squared minus 8x plus 1. That is the x in the f of x function. Or sorry, that is the f of x function. So that's being put in for the x in g. And then we're subtracting the 4. Okay. Number 11 is basically the same idea as number 7, just with 2 other functions, right? F of x equals root 2x plus 5, and g of x equals 3x minus 8. So I'm actually not going to go directly through that one. I'm going to go on to the next problem. Okay, so 23 and 29 I think did trip up a few people. 23 usually went kind of okay. But these are the ones that we're really going to start going through, okay? So in 23, we're finding the derivative, very similar to what we've done before. We have y equals 7 times the quantity 4x plus 3 raised to the 4th power. And at first, we're just going to treat this as though that 4x plus 3, the thing inside the parentheses, as though that were just an x, right? And so when we are taking the derivative of a variable raised to a power, we bring the power down front and multiply, and then we subtract 1 from that power. So I'm going to bring that 4 down front of the whole thing, multiply it by the 7 that was already there, times, if this had been just a plain variable, that would be times the variable, but in this case it's times the function 4x plus 3, and then take 1 away from the exponent, so we now have an exponent of 3. And then this next part is where the chain rule comes in. So if that thing inside of this set of parentheses right here, if that was just an x, we wouldn't have to apply the chain rule. But because that is not a variable, it's a function, we then need to multiply at the end this whole expression that we've got so far by the derivative of that function that's inside the parentheses. So when I have 4x plus 3, what is the derivative of that I need to chain out? Well, the derivative of 4x is 4, and the derivative of plus 3 is just 1. So we don't usually show that part. So that is how the application of the chain rule works. Everything else that happens after that is just simplifying. So we have a 4 times a 7 times another 4. That's 112. That goes out front of the parentheses. And then we have the quantity 4x plus 3 cubed. Okay. 29, very much the same. We have negative 7 times the quantity 4x squared plus 9x raised to the 3 halves. And again, this is the same idea as a variable raised to a power raised to an exponent, but this time it's a function that's raised to an exponent. So we have to chain out the derivative of the inside. So we're going to bring the 3 halves down out front to multiply the whole thing, subtract 1 from the exponent, and then chain out the derivative of the inside function, which is 8x plus 9. And in the solution guide, you can see that's where this next line came from. And then technically at this point, we have actually found the derivative. It's 3 halves times negative 7 times 4x squared plus 9x raised to the 1 half times the quantity 8x plus 9. You could, in theory, leave it like this. And what you'll find with the answers in the back of the book is that sometimes they will simplify and sometimes they won't. So if you get something that looks really different from what the back of the book has, it might not even be that you've made a mistake. It might just be that you simplified to a greater or lesser degree than the book chose to. Okay, so you could actually leave it at this line. I didn't. I took the, let me get a different color here. I took the 3 halves times negative 7 and just distributed it to the inside of the 8x plus 9, that quantity. And that's where the negative 84x minus 94.5 came from. And then the quantity 4x squared plus 9x all raised to the 1 half, that just carries down. There's nothing we can do to simplify those two together because of this 1 half power. Okay. Now, the next one, 37, this is typically where people started having some difficulty. And I think it's because, unlike the previous two, where we were just looking at a function raised to a power, so we were applying both the power rule and then also the chain rule. With this one, we have not only the power rule and the chain rule, but we're also multiplying two quantities together. And so we have to use the product rule as well. So we're applying a bunch of different rules in 37. So hopefully in 37, you can see why we would want to apply the product rule. We have this quantity, x plus 3 squared, times this other quantity, 2x minus 1 to the 5th, and they're being multiplied together, so we've got to use the product rule. Now what I actually did is I just pulled that 5 that's multiplying out front, that coefficient, I just pulled that out front of the whole thing, because when we have a constant times a function and we want to find the derivative, that's the same thing as the constant times the derivative of the function. So I pulled the constant out front and then found the derivative inside of these brackets. Now the product rule says that if this is u, the x plus 3 quantity squared, if that's u, and the 2x minus 1 to the 5th, that's v, we take v times u prime plus u times v prime, or v times the derivative of u plus u times the derivative of v. And then from there, The v just carries down like it was because we're not finding the derivative of that at first. It's just v. Then u prime. So the second part, the x plus 3 quantity squared, we have to find the derivative of that. And we find that by bringing the power down front, making it a multiplier, subtracting 1, and chaining out the derivative of the inside. So that would end up being 2 times the quantity x plus 3. It would be raised to the first power, but that doesn't really change anything. And that whole thing would technically be multiplied by 1 because of the chain rule, but that doesn't change anything either. Okay, so that's the whole first chunk. Then we have plus u times v prime. So u just carries straight down, x plus 3 quantity squared. And then we need to find the derivative of 2x minus 1 raised to the 5th. Power comes down front, subtract 1 from the exponent, chain out the derivative of the inside. So the power comes down front to give us a multiplier of 5. Then we have the quantity 2x minus 1 raised to it goes down to the 4th because we subtract 1 from the exponent. And then we chain out a 2. And I'm sorry, it's really hard to see there because it's right at the edge of my paper. But we have to chain out the derivative of 2x minus 1, which is 2. Now, again, at this point, technically, we have found the derivative. That is it. All of these remaining steps were my attempt to get it to look simpler than how it looked in that step. So let's see, what did I do exactly? Oh, so I took the 5 times the 2 to get this 10. And then, so this 5 times this 2. Then this 5 gets distributed to here, and we had a 5 times a 5 times a 2. So that's why we see the 50. And then from there, I pulled out the common factor of 2x minus 1 to the 4th. I can pull that out. And also one of the x minus 3's is common to both, and a factor of 10 is common to both. So I pulled those common factors out front, the 10, the x plus 3, the 2x minus 1 to the 4th, which means that all that's left in this first term is 1 2x minus 1. And in the second term, 5 times x plus 3. And then from there, I actually combined like terms inside the brackets to get 7x plus 14. And then pulled out a common factor of 7. Put it up front here and combined to get 70 up there, and then the x plus 2 at the end. So again, do you have to do that amount of simplification? No, you don't. But sometimes, again, the back of the book will simplify to a greater or lesser degree. So I like to show as much as I can. But if you stopped before then, that's totally fine. 45 is a very similar idea to the previous problem, except that now we're using the quotient rule instead of the product rule. So in 45, the quotient rule says that we take the expression on the bottom times the derivative of the expression on the top of the original function minus the top function times the derivative of the bottom function all over the bottom function squared. Okay. When we're following this through, the 3x plus 1 quantity cubed, that just stays the same because we're not taking the derivative of that part yet. But then we have the x squared plus 5x prime, right? We need to take the derivative of that piece. The derivative of x squared plus 5x is 2x plus 5. So that's where this came from. Then we had the minus in between because that's part of the quotient rule. The x squared plus 5x, that just carries down. And then we need to take the derivative of the 3x plus 1 quantity cubed. So the 3 comes down front, subtract 1 from the exponent, and chain the derivative of the inside. And so that's what this last piece right here is. 3 times the quantity, 3x plus 1 squared, times another 3. And then in the denominator, when we have the quantity 3x plus 1 cubed, and then we're squaring that, when we raise a power to another power, we multiply the powers together. So that's where the 6 comes from. And again, at that point, that is technically the derivative. We have found it. That is the derivative of that function. Everything else that came after was, again, just me trying to simplify. So I multiplied those two 3's together, those two factors of 3, to get 9. And then I distributed that 9 inside this set of parentheses. That's where the negative 9x squared plus 45x comes from. Since there is a factor in common in both of these terms, we have a 3x plus 1 quantity cubed and a 3x plus 1 quantity squared. So the biggest factor I can pull out is 3x plus 1 quantity squared. So I did that. And then everything else stayed inside of these brackets. And then because we have a 3x plus 1 quantity raised to the 6th in the denominator, those then become a common factor in the numerator and the denominator. So I can cancel 2 of them out of the numerator. And if I cancel 2 of them out of the denominator, there's now 4 left. Then to get to this next step down, I FOILed those two things together. And I distributed the negative sign in there. That's what gives us that numerator. And then I just combined like terms here. And that's what gave us that final version. But again, technically, at this point, we found the derivative. Okay. Then we get to 51. And 51, we're finding the equation of the line that's tangent to f of x equals root 20x plus 5. And we're specifically finding the equation of the tangent line at the point 1, 5. So to find the equation of the tangent line, the f prime, so the derivative of f, gives us the slope of the tangent line. So the very first thing that I did was found the derivative of f, which is 10 times the quantity, 20x plus 5 to the negative 1/2. And then because we specifically want the equation of the tangent line at 1, 5, I plugged 1 into that f prime function to find out what is the slope of the tangent line at that point. And the slope of the tangent line is 2. Then we use our point slope form, y minus y1 equals m times x minus x1. Okay, so then we have y minus, well, the y value of the point that we were given was 5, so y minus 5 equals m, which we found to be 2, times the quantity x minus the x value that we were given in the point, which was 1. And then when we distribute the 2 and add the 5 to the other side, that's where we get this equation of y equals 2x plus 3. Let's see. This next one, we have an equation talking about average mortgage debt in dollars based on the age of the borrower in years. So we're just given an equation. First, it says find m of 57. So we want to find the average mortgage debt in dollars for a 57-year-old borrower. And so we're plugging in the value of 57 everywhere we see an x, and then just crunching that number through. And we find that a 57-year-old has an average of $45,000 in mortgage debt. Then we find M prime of X. So again, you can see here I've taken the 2, brought it down front, chained out the derivative of the inside, and then the derivative of the constant term is 0. So that's where we get this negative 2, 10x minus 470 times 10. And then I just cleaned it up a little bit from there. I multiplied the negative 2 times the 10 to get negative 20. And then in parentheses, 10x minus 470. And then distributed the negative 20 inside and simplified as much as possible. Then in part C, we're finding M prime of 57. So now we're finding, rather than the average mortgage debt, we are finding the rate of change of mortgage debt when someone is 57 years old. So we're plugging that 57 into the M prime function. And when we do that and crunch the numbers through, we get a value of negative 2,000. So that tells us that for 57-year-old borrowers, on average, mortgage debt is decreasing by $2,000 a year once they're age 57. Let's see, 59 is fairly similar to what we just looked at in 57. We start by finding the marginal revenue function, which is just the derivative of the revenue function in part A. And then we take that marginal revenue function and we plug in several different values for X to find those marginal revenues. And then in part C, we can see that as the number of items sold increases, our marginal revenue is decreasing. We're making less. Let's see, 67, we're finding a derivative in part A. So again, we're going to bring that power down front, make it a multiplier, subtract 1 from the power, chain out the derivative of the inside, which is 1 over 1200. And then you can simplify that here. 24 times 24,000 times 1 over 1200, that's where this 480 comes from. And then inside the parentheses, 1 plus r over 1200, that whole quantity raised to the 23rd. And that is our derivative of A with respect to r. In part B, find dA dr when r is equal to 2 and interpret your answer. So we're just plugging 2 in there for the value of r and crunching the numbers. Should come out to about $498.74. And what that tells us is that the balance in the account is increasing by $498.74 by increasing the interest rate from 2% to 3%. So when we have a rate of 2%, if we bump it up to 3%, the balance in the account would be increasing $498.74. And then on our last page, we're dealing with marginal revenue product. For a manufacturer with 10 workers, we've got a demand function, P equals 200 minus X all over 4, and X is equal to 6N. So then here's our equation that we're working with. dr over dN equals, in parentheses, P plus X times dP dx, all in parentheses, times dx dN. So then we want to find each of those various quantities. We have an equation for P that was given. We have an equation for X that was given. So then the two things that we need to find are dP dx and dx dN. If I go to the equation that's P equals, and I find the derivative of that with respect to x. Another way of looking at this function is 50 minus 1/4 x. That's actually the same thing as 200 minus x all over 4. Well, the derivative of 50 is 0. The derivative of negative 1/4 times x is just negative 1/4. So dp dx is negative 1/4. Then to find dx dn, I'm going to go to my x function over here, x equals 6n. Find the derivative of that with respect to n. Well, it's just the 6. So dx dn equals 6. And when we have 10 workers, we know that if x equals 6n, and n is the number of workers, then when we have 10 workers, x is equal to 60. And so then we're just plugging all of these things in. I know that's a lot, but again, if we're looking at what our formula here says, it says we start by plugging in the function p, that's this, 200 minus x all over 4, plus x times dp dx, which was negative 1/4. And then outside of all of that, that's all inside of its own set of grouping symbols here. Outside of all of that, we're multiplying by dx dn, which was 6. And then from there, we're kind of simplifying as much as we can if you want to. Here, you don't actually need to simplify if you don't want to, because we also know that we're going to be evaluating this for a value of 60 for x. So you could skip the simplifying and just plug the 60 in for x. But I simplified this whole thing down to 300 minus 3x. And then when we plug in the value of 60, we find that dRdn is equal to $120 per worker. So hopefully that helps with all of these. If you still have questions on 11.7, please feel free to just send me a message, and I'm happy to discuss any of these problems in more detail.